All right, welcome everyone. Good morning, good afternoon, good evening. We'll let people trickle in. Glad to have you here today for Karl Kappler's talk. But before we get going, we'll just do a quick overview. So just a reminder that all of the previous EMinars are accessible on the MTNet website. So you can access both the recordings as well as slides if presenters have chosen to share that with us. And then there's also the registration links for any of the upcoming EMinars. And up next week, we have an Andrew Ray on Julia-based geophysical optimization and Bayesian inference. And so that'll be an hour earlier than today's presentation. So be glad if you're able to join us for that. And as mentioned today, we're glad to have Karl Kappler here. He'll be presenting on, are there electromagnetic or precursors to earthquakes? 2 statistical studies from the San Andreas Fault. So really looking forward to this presentation. So I'll give Karl a quick introduction and then pass things over to him. So Karl is a senior geophysics scientist at IMDEX, which is a global mining technology company. He's held roles in development of remote sensing and digital data processing, mostly in EM and acoustics. Karl's research has included projects in ultra-low frequency EM, UXO, resource exploration, borehole investigations, and measurement well drilling. He has his BSc in math and physics from the University of Victoria, just across the water from me, and his MSc and PhD degrees in engineering geoscience from UC Berkeley. Karl's an active contributor to the open source Aurora magnetometer processing software, and this is connected with the SIMPEG project, as well as USGS maintained packages, including MT metadata and MTH5. And when he's not setting the global electrical circuits, he tries to stay out of trouble with yoga classes at the Y and hiking. So good choices, Karl. So with that, I'll pass the screen share over to you, and thanks for joining us today.
Okay, so sharing screen. Okay, so I'm going to try to set my view to slideshow. And can I get a quick thumbs up or down?
That looks great, Karl.
Okay, great. Okay, thanks. So, okay. Thanks for being here. Appreciate it, and for the opportunity to. Sorry, is the screen showing a bar on the left side, or is it showing the full slide?
It is showing the bar on the left side. I think if you just click on the slide, you should maybe get rid of that. Yeah.
Thank you. Okay.
Looks good.
Okay. So, okay, thanks. So, okay, I want to talk about this kind of project that I've been involved with on and off over several years. And it's about this investigation into whether or not there are geomagnetic or electromagnetic precursors to earthquakes. So on the left, you'll see a sort of whimsical cartoon. And on the right, that's actually an article that was out in New Scientist this month. About 2 weeks ago, it came out. Just talking about this project or the project that was at QuakeFinder. And so I want to just basically talk about 2 manuscripts that were written during the time that I was at QuakeFinder. And so that's the highlight of this talk, and it's the point, is to distill those papers down into a summary. So I'm going to give a quick background of the project that is at QuakeFinder and the research work that was done, and the array and research objectives. And then I'm going to talk about a paper we wrote at QuakeFinder and a follow-up paper, or actually an independent analysis, I should say, that was done by the Google Applied Sciences team, and then summarize that work and give a quick state of the array today. So QuakeFinder, what is it? It's a private, basically a project. It's a satellite systems engineering company, and they started around 20 years ago this humanitarian R&D project in order to address the question of whether or not there were electromagnetic precursors to earthquakes. So that's been it's been an ongoing project, and I my shift was sort of between the spring of 2016 and the summer of 2018. And I was there when we had a lot of data. So, and then the other team that's relevant in this talk is the Google Research Applied Science team. They call themselves the GAS team, and they analyze the QuakeFinder data independently. And they, of course, have a lot of computing resources, and they spent basically a couple of years on that work. So, okay, so the quick obligatory, what we'll talk about and what we'll not talk about. So the objective of the array is to look at electromagnetic data, in particularly in the context of earthquakes. And it's motivated by reports of anomalies in the literature. You can query the literature and find everything from, you can find some very exotic phenomenon reported and less so, but I just have a little figure there on the side. That's an anomaly that was reported in California right before the Loma Prieta earthquake. And that was the 1989 magnitude 6.9 that was right near San Francisco. So the question that the array tried to address is, are short-term forecasts possible? Is there physical evidence supporting it? For what it's worth, the figure that's shown here has been widely criticized, and then there's an ongoing debate in the literature about these anomalies. So today we're going to talk about two recent publications based on the QuakeFinder dataset. We're not going to address operational forecasting. We're not going to have the time to cover possible physical processes that could generate the signals, and unfortunately not give a review of very interesting efforts underway that include especially in Japan, Italy, and Greece, and in China. So what we have today, right, are there's basically two systems out there. There's the short-term early warning systems, and I can testify to the value of those. So we had last year a good-sized earthquake in San Jose, and my phone buzzed and told me to expect strong shaking or moderate shaking in about 10 seconds, and that's what happened. So it's pretty cool. And then there's sort of decades of warning systems, so working with probabilities and drawing maps that are used for informing civil infrastructure. In the middle is the question that QuakeFinder is wondering about. Is there the possibility to forecast with days or weeks of warning? So the QuakeFinder effort is basically, it's a pretty substantial array. So on the left, this is what a station looks like. So it's just a solar panel with some comms boxes. And on the right is the footprint of the array. So that's pretty much the state of California, with faults shown in black lines. And the dots are where they're stationed. So it's a substantial array. There's around 125 stations. They sample continuously at 50 hertz and relay the data back to a data center. The magnetometers are buried about 15 centimeters below the surface to reduce noise from vibration. And there's 3 induction coil magnetometers at each site pointed in north, south, and northeast and down. So the instruments themselves are, as I said, induction coil magnetometers, and there's 2 flavors of magnetometer in the array. There's another one called the QFido2, but it's been phased out and was never really used much. So they're mostly ANT4 or QFido3. So your ANT4 is an exploration grade sensor. And then the QFido3 is a similar concept sensor, less expensive and noisier. So the ANT4 is like an order of magnitude below the natural field vibrations. And then the FIDO3 is approximately at the natural field background for a lot of the spectrum. And so that's what I want to say about those sensors. So if you've not looked at these sorts of time series, this is just a graphic to show what they look like. So they're wiggly little lines. And on the upper left, you have got, this is a 24-hour time series. And this is from a publication that San Wang did when she was a visiting scholar at USGS a couple of years ago. And so the red, blue, and mustard colors there are 3 coils at the same station and just doing a side-by-side analysis or noise level comparison. And then the lowermost time series is a fluxgate magnetometer, and that's from the USGS or from the global array, and that's at Fresno, California. And then in the bottom right-hand corner, you can see a map showing it's about 250 kilometers between stations. So what do we see? We see that the 3 coils that are all at the same location, they all have very similar time series, which they should. But you can see that they're very noisy for much of the day, and then they get quiet for a few hours. And so that's the DC electric train system. That's the BART system operating in the Bay Area that noises up all the data for a while. But in the dead of night, which say around 11 o'clock UTC, here in California, they all see things that are pretty similar. And so on the right-hand side, pardon me, is just a zoom of a trace or an event that's seen in the global geomagnetic field. And the takeaway is that the signals are extremely similar if distances of hundreds of kilometers away. So that's that's just to give a context of what is the data that we're looking at. So coming back to that, we're going to talk about 2 papers. So the QuakeFinder array has you get 125 stations or so, rounds out to around 70 terabytes of data. And both of the papers, I'll just mention here, reduced the data because it's a lot, to total field amplitude. So square root of the sum of the squares of the of the different magnetometers. And so that results in at least cutting the data by a factor of 3. So both of the studies I'm going to talk about were about basically trying to extract signals from the noise. And the first study was in time domain and used a short-term average, long-term average filter, and it worked station by station. And then the second study we're going to look at used cross-spectral power between the stations. And both studies were geared at answering the question of, is there a statistically significant ultra-low frequency magnetic signal before earthquakes? And we worked in the context of qualifying events by being larger than a certain threshold and closer than a certain distance threshold to the stations. And those will get described in more detail. Okay, so on to the first paper. So the first paper, this one was published in 2019. We wrote it in 2018, and it was basically a way to process data. We had ambitions to process data many different ways. So we came up with a fairly generic framework, which just took the time series data as input, resampled, got everything to the same, so you can put it all into arrays at the same sample rate. We had imputation or masking, filtering, and then there was this thing we called a signal finder, which is essentially just feature extraction. And then in this specific instance, we used this STA-LTA filter as our feature extractor. And then we used some sort of a scheme for ranking, which I'll describe. And then we evaluated the performance of the algorithm using receiver operator characteristic curves, which will also be described. So this was the high level flow. And I'm going to describe with graphical help what we did, but I just want to take a minute here to go through the key concepts that are going to keep coming up in explaining this. So we have the idea of a station day, and that's just how we chunked the data in order to analyze it. So a station day is basically a UTC day of data acquired at a particular station. And there was about 200,000 of those in our study. We got this concept of a magnetic field pulse. which you can think of as a spurious transient signal in the magnetic field time series, such as that we looked at a couple slides ago, something that stands out against the background. And then we have this idea of counting the pulses. So we used a short-term average, long-term average filter for pulse counting. And we worked with a sliding window variance. And basically what happened was for each station day, we wound up with some integer number of counts. Okay, I'll get into the details later of how that was done. And then importantly, we have this thing, this quantity of normalized pulse counts. And so as we saw in the time series slide, the background noise levels of the stations are quite different. So we normalize the pulse counts in order to be able to compare between stations. And we use the previous 100 days median. And then there's this idea of ranking. So every station day, we assigned it a scalar value. And it was basically the number of normalized magnetic field pulses over the previous 4 to 12 days, or basically, you know, how pulsy was the magnetic field the week before last is how you could think of that. And what this allows you to do is then rank the station days against each other. And then remember, the hypothesis that we want to test is whether there was an increase in the normalized pulse counts before earthquakes or not. Those are the key ideas in the manuscript. So basically, we started with going to total field with the time series, and then we took a 3-second window, and slid it across the time series, computing the variance, and that's at a 75% overlap, and that reduces the data by a further 40x and gives us a time series of magnetic activity, what we called. And then now, so that's basically, you know, when there's a spike or a step in the data, that value is large, and when there's not much happening, it's small. And so to find things that stand out against background, we basically took the A of t time series and just normalized it by its surrounding values, or basically a low-pass version of itself. And that's a standard filter that's used to pick out spurious events. And so that's how we wound up distilling the data into something that we could work with. And we worked in the logarithm of the quantity. And I'll show, so here's a time series on the left of, these are your STA, these are the log of the STA, LTA. And the mean is shown in a blue line, and then the magenta line is showing the threshold above which we counted events. And then on the right is a histogram of the same quantity. And so you can see why we'd work in log space. You get sort of a nice bell-shaped. So for every station day, this quantity was computed. And so we get this integer pulse count for each station day. And then I'll said it before, but I'll say it again. Because of the site-specific noise environments, we normalized those counts by the 100-day moving average of the daily pulse counts. And so this gives us numbers that are around 1. And this is the key feature that went into the algorithm. Okay, and then the ranking is associating with each station day the number of normalized pulse counts from the previous 4 to 12 days. So here's a graphic to kind of get that across. So if we want to assign the ranking for a particular day, which I'm denoting as this box with an R and a star in it, how we would compute that number is we would go back 4 days, and then we would sum the normalized pulse counts over this hypothetical precursory window, which is 8 days long. And then we would normalize that by 100-day normalized pulse counts leading up to it. So what that's saying is, you know, it's 8 days, but call it a week. Is that week standing out more or less than the last, say, 3 months or 100 days? Okay, so that's the ranking. And because the ranking for a day is generated by data that's completely acquired 4 days before, you could issue this number or look at this number before the day happens. And so the data packets that come out of this now are pretty small. So for every station day, we essentially have a station identifier, we have a date, and now we have our ranking number. Okay, so those are the data packets that come out of this. And so then in order to analyze whether or not these rankings wind up ordering the station days in some way that's so, and just one last thing about that previous slide, there's no mention of earthquakes here, right? Yet at all, okay? So the earthquakes come into it when we do the hypothesis test. So the way I think about this is you write the ranking information on a card, and now you rank those cards by the you rank those cards based on that ranking number, and then you draw a rock curve, okay? And how you draw a rock curve is you start at the origin, and there'll be, say, some 200,000 notches on the x-axis for days without earthquakes nearby that station. And then there'll be, in this example, there's 180 cases where there was an earthquake near the station, greater than magnitude 4. And then what you do is you start flipping over the cards one at a time. And if the card does not associate with an earthquake, you move to the right. And if it does associate the earthquake, you move up. So if by some chance all the earthquakes were at the top of the deck, you'd move straight up and across, okay? And so what this does is so if you've just had a random arrangement of the deck, what you'd expect is after you've turned over half the cards, you would have seen half of the earthquake cards. And after you turned over 3/4 of them, of the cards, you'd have seen 3/4 of the earthquakes. So this green line is called the chance line. And so basically the area that you trap between your realization or your curve and the chance line is related to how far you deviate from random. Okay, and so you can map these numbers directly onto z-scores. And importantly, it depends on how many earthquakes and how many non-earthquakes you have in the set in order to get the mapping between area under curve and the z-score. So this was a result that we've got for magnitude greater than 4 and distance less than 40 kilometers. This was the ROC curve we got, and that gives a z-score of 2.2 sigma, which is better than 95% rejection of the null hypothesis. That was our result. That's the official result of the study, because that's what we set out to test. We did try removing the worst stations. I'll mention why in a minute, but in that the score bumped up to 2.86 sigma. And then for what it's worth, after we published the paper, the USGS updated the earthquake catalog. And so we just, changing nothing else, we updated the earthquakes and got a 3.06 sigma result. So that's pretty cool. Why did we throw out some stations? So the Pacific DC intertie is a power line bringing power to Los Angeles area from Washington State. It's a DC power line that's fluctuating. And the data in the stations that are near to it would if you're a magnetotellurics person, you would look at them and you might describe it as garbage. It's really noisy. So and it's got spurious transients all the time, driven by processes that are not basically geo-sourced. So we did a heat map of hypocentral distance versus cutoff magnitude, and essentially found that, around magnitude 4 and around 40 kilometers distance is where the algorithm seemed to give a statistically significant result. And I'll just mention that there's some sort of opposites observation here where it's darker blue, and so that would almost be saying that there was fewer transients in the magnetic field if the earthquake was, say, 80 kilometers away and large. For what it's worth, those blue squares attenuated significantly when we removed the Pacific DC intertie data. So, and just as a guide for this, here's the number of earthquakes corresponding to each cell in the bottom right corner. So that's why there's not very many quakes in the upper right, because we weren't very, very close to very, very large earthquakes. So in summary, we basically analyzed total field using some kind of a pulse extraction method, and did a rock analysis, and basically got a 2.2 sigma that went to 3.06 with the latest earthquake catalog, and removal of the worst stations. And I'll just mention, I guess, that we didn't do properly a train test split, but we did optimize the selection of the 8-day window based on a smaller test case of a much smaller data set. So there was something of the spirit of a train test split involved in that work. Okay, so that's the first paper, and now the second manuscript. So this was called Case Control Study on a Decade of Ground-Based Magnetometers in California. Reveals modest signal 24 to 72 hours prior. So in 2017, we met with the GAS team, the Google Applied Sciences team, and presented the research. And so they are kind of like the A team of data science, I guess. If you can find them, maybe you can get them to help you. And so we presented our work and waited to hear back, and they agreed to look at our data and perform an independent analysis. And they spent a couple of years on that, first doing exploratory data analysis, which was a lot of crunching, I think 1 billion compute hours, but eventually deciding on this case control framework to analyze the data. And then the writing happened in 2020. So once again, we're gonna just do a key concept, and then I'll have slides to illuminate some of this. And the graphic in the upper right, the project was called Project Namazu, as a nod to the mythical catfish in the Japanese lore that causes earthquakes. So they worked with the same data, but they worked in frequency domain. And where the previous study had done things kind of one station at a time, they importantly isolated earthquakes that were close to 2 stations and only worked with those. And then they used cross-spectral power amplitudes. They used a train test split, and it was very formal. There was no looking at the test data until training was done. And then the case control framework is essentially for each earthquake, there was again defined a hypothetical precursory interval, and then a collection of hypothetically quiescent intervals. And then from those intervals, features were extracted. And then the question was, is there a separation? Are the distributions of these P features and Q features different? So linear discriminant analysis, or LDA, was used for that. And then that's what's done on the training set. And then that LDA set of coefficients is applied directly to the test set. So what happened was, at the end of the training, the test set was run, and the Z-score was 2.1 sigma, which is kind of interestingly close to the 2.2 sigma that we got in the previous paper. And then, like in the previous paper, where one test was done later, one observation was to detrend for global geomagnetic activity, and this changed the results in a significant way, towards more significance. So, okay, the case control framework. So how was the problem approached? The data were chunked into these, in our case, we used 48-hour intervals. And so for each earthquake that was going to be studied, this 48-hour interval that happened 1 to 3 days before the earthquake was tagged as the hypothetical precursor interval. And then moving back in 2-day-long chunks, the other times were tagged as hypothetical quiescent intervals. And again, we want to measure the distribution of these P features versus Q features. And so there's a couple things that this framework does is it greatly reduces the amount of data that you need to analyze. It controls for geography in the sense that you're comparing the same station pair against the same station pair over and over within a particular analysis of a particular earthquake. And it somewhat controls for long-term effects because these signals aren't stationary, so you wouldn't have seasonal effects here. Another thing just to mention with the 48-hour period, you get it's tagged to the diurnal cycle, and then by using, which is to say that you wouldn't get spoofed by time of day effects because they're averaged into each period. And then you also account somewhat for time of week effects by having these 2 weeks of quiescence to compare against. So that's what we want to say about the high level approach and the framework. And so I'm just going to describe how the data were processed. So it started with a train test split. And the data were split approximately in half, and that's volumetrically. So you can see that the first acquired data by the QuakeFinder array was 2005. But the array grew over those years and really came to its full size around 2013 or 14. And that's why the test set was only about 3 years long and the training set was around 10 years long. And this is a natural way to split the data because it's data from the past being used to train a model and then apply it to future observations. So it was done by looking at the USGS earthquake catalog and the QuakeFinder station locations, but not by looking at any QuakeFinder data. And reporting, the reason to do this is that you're preventing model overfitting. So you fit your model to the train, and then you report the results on the test set. So so basically you'd need to be fooled twice, once by the train, once by the test, if you were to report a result that was incorrect. So the next step in the data processing flow was the selection of sites and earthquakes. And so you start with the USGS catalog, you filter the earthquakes that are less than 3.5, and then we identified site pairs. So these are pairs of QuakeFinder stations that are less than some distance apart. And we parameterized that distance with theta. It was around 30 or 40 kilometers. And then the next thing that you do is then filter so you now have site pairs. Now for each site pair, you find earthquakes that are close to the site pair. And so that was done. And then you filter based on the magnitudes of the earthquakes, which gives you another parameter. And finally, we applied a declustering rule. So the declustering rule filters out earthquakes for which there was other earthquakes of large magnitude in the hypothetical quiescent periods. So we basically tried to find, you could say, clean examples of earthquakes that didn't have a bunch of other earthquakes in the time periods that we were hypothesizing as quiescent. So that's how the data set was selected. And then moving, so in the last 2 slides, we've gone over these period lengths that were 48 hours, the buffer period, which was 24 hours before. So we called these things tuning parameters. And in the manuscript, there was 3 tuning, we called them tuning conditions, which are fixed collections of tuning parameters. And the names of these tuning conditions, as a nod to Namazu, are varieties of catfish. So blue, channel, and flathead are the 3 tuning conditions that were looked at. And for what it's worth, every tuning condition that was defined was reported on in the manuscript. And so we'll look at the results. And then the other concept here that pops out is this notion of an SSE. That's a station earthquake tuple. So remember, there was only 10 earthquakes in the training data set, but there was 55 SSEs, because if you have several stations near an earthquake, you can pair them up differently. So that's how we selected the data for analysis. Now, feature extraction. So for each, okay, back to this concept of these different periods that we showed, for each hypothetical precursor period, basically we computed spectrograms, or they computed spectrograms, and chopped the spectrograms into 85 log-spaced frequency bins. So you wind up with this sort of 48-hour spectrogram, and they also work, by the way, with the log of the data. And then basically within each frequency bin, they selected the 98th percentile of data. So what does that mean? It means that it's distilled these, some 25 million samples of data per period down into a single vector of 85 numbers, where each of those numbers is the 98th percentile of the cross-spectral power at that frequency for that period. So that's the feature extraction that was done. And just for in passing, the precursor period does have one property that biases it somewhat, which is that it's the latest in time. So if there was some kind of drift in the sensors, or noise levels were just generally increasing in time as time moved forward, that's a potential source of bias. And so the features were actually detrended with respect to time, just with the slope, not with the intercept. And the details are in the manuscript, but essentially we referred to that as the pocket watch principle. And we did take measures against it. And so that's all I want to say about that. Just a quick sanity check here on cross-spectral power, right? The idea is that you have these two sensors that are located, some 35 kilometers away from each other. And so if there's signals that are at only one station, like a car driving by, what'll happen is there'll be, more signal at that station. Whereas if there's signals that are common to both stations, if you multiply the spectral power together, you get a much larger amplitude in your cross power. So essentially, this is a way of amplifying signals that are common to the different stations. And there's a sort of a numeric example multiplying them together. Just to, in this example, the pulsation, if it was 3 times larger than background, 3.5 times larger, then the cross-spectral power winds up being 10 times larger than the cross-spectral power background. So okay, so how are we going to actually quantify the separation between the P and Q data sets, or these two distributions, these features that have been extracted? So we use the signal to noise ratio concept, which is essentially the same as measuring the number of standard deviations that the histograms of the two different quantities would separate by. And so the SNR is that's essentially the question that we're just trying to answer here is, are the two distributions distinguishable, and by how much? And so the SNR, signal noise ratio, quantifies that. So, okay, we used linear discriminant analysis in order to do this. And the key thing here is that it's essentially just a way to pick a set of weights, which we call B. We want to search for a set of weights that have the effect of separating the P and the Q frequency vectors. And there's normally you seek the weights to optimize the signal noise ratio or maximize the separation of those P and Q features on the training data set. That often involves regularization. And what we did was to simplify things, instead of worrying about regularizing, we actually just used the difference between P and Q, okay, the average difference between P and Q as the LDA coefficients. And so what we actually wind up with is here are the LDA coefficients that we got. So this is what happens with the training set. So you wind up with curves that look like this, and the shaded circles are a smoothed version, whereas the open circles are the raw results or the raw P minus Q differences. So there's a couple things to notice about this. One of the first things is the three curves from the three different tuning conditions are quite similar. And that's not surprising because the three tuning conditions weren't wildly different. You know, there was only a small difference in the magnitude threshold and in the distance threshold. So there's a lot of cross data between them, but it's reassuring to see that they're fairly similar. Another observation is that they're reasonably smooth. So we smoothed the coefficients before we applied them, which makes them, I guess, makes the separation on the training set a little worse, but hopefully a little better on the test. But even before the smoothing, you can see a kind of shape to them. And I think a really important observation here is where that peak is. So that peak is pretty much smack between 1 and 10 seconds period. So that, as MT practitioners know, is the notorious dead band, where you have basically very little, if any, natural signal going on. So it's pretty interesting that with no assumptions whatever about the fields, just taking these cross spectra and then differencing P and Q, what shakes out is a curve with this shape. So yeah, so those are the coefficients. And again, there's the dead band. So it's around 3 seconds is the very center of the peak. So and that area is where the Q minus P was large. Okay. So what we do with those then is we use those weights and we apply them to the test data. So no one's looked at the test data until after those coefficients were computed. And those coefficients, there's a couple of variations in the study that are described at the end, and those variations, the coefficients were never recomputed. So here are the test set results, and you know, the actual results, if you were to boil it down to a number, is this little looks like a Star Wars fighter here in the upper at the very top. And that is your signal noise ratio plus or minus 2 standard errors. And remember, importantly, if you want to compute a Z-score out of that, you take your signal noise ratio and divide it by 1 standard error. So that's how we get our probabilities or Z-scores. And so that's really the results. And then we further broke down the box plots into the different earthquakes that were in the different test cases. And the heights of the boxes here are proportional to the square root of the number of observing station pairs. So the taller boxes, if they weren't square rooted, would be really large or would be really tall. So essentially what you see is that there is a tendency for the boxes to lie to the left of the line. It's not particularly overwhelming, but it's there. And if you want to quantify it, you take the signal to noise ratio, and that's what, you know, that's what tells you how far left or right the total sum of all the boxes is. So the results that we got on the test set It's not very significant, but it does support the rejection of the null hypothesis at a 2.1 sigma level. And again, this is the test set, right? The trained set Z scores were much higher. This is consistent with the history of anecdotal observations, right? If there was something really obvious happening, we wouldn't have spent all this energy looking for it, right? So and so the question when we were working on writing this up, we were like, well, what are the reviewers going to ask? And one of the things that came up was, well, what about natural variations? Could we be could this be having an effect? Because we know all of our stations see the natural global geomagnetic variations, and importantly, because of spectral cross power, because those are at all stations, those are going to get amplified. So what if we could take our features and then fit a line, say with AP to them, and then detrend the features to the AP line? And so we did that. And this is what happened. And it's hard to put the box plots right side by side. So I just pulled out the blue tuning, which is I guess the least dramatic change. And again, I circled here or boxed here in red is the TIE fighter, which is the result of the test. And so you can see it really moves to the left, right? It basically doubles the SNR, and that basically doubles your Z score. So, after applying this correction, which no retraining, no new coefficients, just try detrending the features and run everything else as it was. And the thing that happens is all of the blue boxes, which were previously en masse to the left, but when you look at them, some are right, some are left. After applying this AP correction, all the boxes are somewhat to the left. So it's a pretty intriguing result. And again, it kind of suggests, it's very physical, right? We did something that made physical sense. Yeah, there's a caveat on that slide. There's some more details in the detrending that we don't really have the bandwidth to get into, but they're discussed in the paper. There's a table called table S8. If we have a discussion after, I'm happy to show it. But we do describe every variation completely that was done with the data in that table. But remember, we did do the KD trending as well, and that's also involved in those slides. In those previous two figures. So to recap this study, the data were split into a training set and a test set. Pairs of stations near earthquakes were isolated. Those were cases. And then data was basically distilled into the cross-spectral power were computed for each chunk of data and features extracted. And at that point, we defined quiescent and precursor periods, and then used training data to try to distinguish between the P and Q, and then directly apply that linear discriminant analysis to the test data set. And so summarizing both papers, so there was two independent statistical analysis of this magnetic field data. There was a time domain study that suggested a shift in the histogram of STA LTA in the 4 to 12 days before earthquakes happen. There was a frequency domain study that suggested an increase in the 98th percentile of cross-spectral power in the 1 to 3 days before the earthquake. Both studies got baseline results of greater than 2 sigma, which is greater than 95% confidence rejection of the null hypothesis straight out the gate. And then both of them improved to over 3 sigma with what we'll call simple reasonable algorithm enhancements. So it's important to emphasize this is not sufficient, not even close for practical forecasting. And there's no claim that this is, but I do claim that this is evidence that's pointing towards the existence of an effect that should be studied further. So, and just one slide I want to show here, just thinking about further studies. So this is the two different the two studies with the hypothetical precursor intervals colored in the pinkish and the hypothetical quiescence in the vanilla. And the idea to get across here is that they were actually different intervals, and it makes one wonder if there's not a way to combine the two methodologies and maybe do better. So that's something. And so just to say, where is the QuakeFinder system at right now? So it's on life support. Despite these, I'll call them intriguing results, there is no plan for follow-up research. Maintenance of the array and analysis of the data is beyond what Stellar Solutions can handle, despite the Herculean efforts of John's Herculean efforts in keeping the array running. So that the QF network is basically likely to be decommissioned, and it would be great if that could change. So one thing that hopefully could be stimulated would be discussions for other applications of the array data, or maybe people would like to use the array data for some maybe a follow-up study. And that's what I had to show. So there we go.
Thanks, Karl. Some fascinating and stimulating discussion here. Things to definitely be thinking about. So I'll open it up for questions. If anybody has a question, you're more than welcome to just raise your hand in the Zoom thing, and I can invite you to actually come and ask your question of Karl directly. I see there's already actually a couple of questions in the chat. So from Valeri, one of the questions, so I know you mentioned this was outside the scope of the presentation, but curious, and I'm curious about this too. So any hypothesis about the physical mechanisms of magnetic precursor generation? So I'm sure that's a whole other topic, but if you have some thoughts or short notes you could share with us, that'd be.
Yeah, so in the, sorry, I'm hopping around here.
Yeah, no, go for it.
Hearing for a second. Let me see if in the supporting material, we actually we did get we did dedicate a couple thousand words to that, or around 1,800 words to that. We had a section on physical mechanisms, and there's some popular ones out there, and we basically wound up with two mechanisms. One of them is streaming currents. So that one's possible, and there's a one reason for. I'm actually going to stop share. I'll restart if there's a so one of the streaming current method was one of the reasons it fell out of favor is because it had a signal. The argument was, well, the signal level won't be much larger than natural fields. And but interestingly, that's what we see. We see something that's, our signal noise ratio was, after APD trending, it was about the same size as the natural fields. The other thing is the streaming currents could conceivably cause vertical electric fields, which could conceivably cause ionospheric disturbances, of which there's a lot of interesting work in the literature happening, which I did touch on. So streaming currents, and then the other one is galvanic, which I really like, which is the notion. So Gary Egbert put out a paper on this, and the idea is it's basically the idea that there's, the natural spectrum goes up so much as you get towards the long periods. So the idea is that there's always, at low frequency, there's always pretty big currents that would be ready to flow. And then the idea is that as a fracture, say, periodically opens and closes, if a conductive environment appeared for a little while and then disappeared, it's not that the currents are being generated by any magic process. They're already, there's the electric potential is already there. It's the periodic appearance of a channel that they can flow down that causes that. So those are my two favorite. But there's, you know, it's anybody's guess, and we really stuck with in these papers that it was data driven, right? We tried stuff and then reported the results statistically. So
Excellent. Thanks, Karl. The next question I see coming in is from Lingaroo. Apologies if I'm mispronouncing your name, but thank you. And they're asking then if there's any comparison with the traditional way of probabilistic or any other forecasting. So if there's been sort of any other studies that you've seen that perhaps promote some consistency with the results that you guys have obtained.
So, well, yeah, I'm not sure how to attack that. When we came up with the rock curve analysis, and I mean, we basically from reading Zekar and Jordan, which is basically this is research coming out of CSEP, the Center for the Study of Earthquake Predictability in Southern California. So we looked at a lot of their papers and we tried to make statistical tests that followed what they were doing. So we did try to follow the literature, but it's, yeah, I'm not sure what else to say about that.
Thanks. Another question coming in, was there work done on optimizing the choice of precursor time? For example, maybe it's 1.5 days before the earthquake when the largest natural signal is generated. So has there been work done on that?
Yeah, no, there hasn't. And so there was some tuning exploration that was done on the training set. But basically that, I think that's an important thing to bring up, because in order to do the statistical test, you need to lay down these rules, and you know, you have to say things like 1 to 3 days, right? But what if something was happening a little before or a little after, or and you know, the disregarding of the 24 hours before the earthquake was done you know, so that there's no confusion about the data that's going into the algorithm, right? But using that data, I mean, it's pretty tempting to revisit the data set. I think there's, you know, I think there's a few theses here that could be done, especially in the modern, you know, in the computing world that we live in now, which even, you know, 2017 was 6 years ago, right? So, you know, the tools that we have, I mean, I was just learning TensorFlow as I was leaving. It's that there's other things to try, and optimizations in, you know, these things. That study provided a framework, another framework to work in.
Excellent. Actually, you touched on something that's another question here comes in on Casti. So if you could expand a little bit on why you didn't use the 1 day before.
So there was a couple of reasons, and but one of them was that the time interval would actually be valuable beforehand. So it would be, if you know, one of them was to make the time interval before the earthquake long enough that it would be useful to have that kind of warning. But honestly, so this was decided by the gas team, and I can't remember all the details of. We talked about it more than once, but I mean, it's pretty tempting to do the analysis, and they did. By the way, they did consider using a gap of 1 hour. So if you look at the, let me just share again here. Sharing my desktop. So if you can see,
Yes.
Okay, just a second here. Sorry, it's down here. Yeah, okay. So I breezed through this one quickly, but there's the parameter, and so the parameter that we're talking about right now is called the buffer period. And we called it in our study, we call it the gap. And so the value of 1 hour was considered in the tuning grid. And I hate to keep pointing to, but that is discussed in the supporting material. There is a section called the tuning grid. And but I'm not sure what it said and why the decision was finally made to go to 24 hours instead of 1. If that was a better SNR on the tuning grid, or whether that was a decision about the practicality of the forecast.
Thanks, Karl. A couple of other questions kind of on the mechanism. So there's a question here. What about microfracture electrification effects as a mechanism for pre-seismic EM signals?
Why not? Why not? I mean, you know, so yeah, like there's a lot of models out there, and you know, there was in our little discussion, we covered 4 of what I'll call the classical models. So piezoelectric, piezomagnetic, streaming currents, and these galvanic effects, and basically ruled 2 of them out, and the other 2 were we can't say. We tried again to avoid getting into it because it's a whole nother topic than the data driven, you know, analysis that we did to just answer the question of what happens if you process this data and just ask the question, you know, where do you land in the statistical answer? What are the odds of getting, you know, the results that we got? But yeah, so definitely there's fractal emissions, and you know, there's questions that lie more in the material science side of things. And I don't have the answers, but I think they're really interesting to discuss.
Thanks, Karl. 2 other questions I see here. So a question from Esteban. Any idea if there's a signal in the polarization of the magnetic fields during the spike? I don't know if you looked at all, if it tends to be, you know, oriented towards or orthogonal to epicenters or noise sources.
Yeah. So there's another follow-up study that should be done, right? Because both of these studies boiled the data down to total field, not because there's no interest in looking at the directions in which the fields are pointing or polarizations, but only because, you know, you had to start somewhere, and it's just like, you know, we tried to start as simple as possible. So there hasn't been any polarization analysis, and I encourage it.
Thanks, Karl. I'll ask another question here, and I think your previous statement perhaps has answered this, but just so it's on the record. So from what you've said, I understand the magnetic field is not taken into account at stations more than 40 kilometers away from the earthquake. But in large earthquakes, for example, over magnitude of 6, more distant stations might also be considered. I would suspect from your previous answer, it's a choice of cutting data, but if there's anything you'd like to add to that, go for it.
Yeah, no, that's it. It's so we don't have that many really large earthquakes in California. Even with this decade plus of data, you know, there was actually, if you go to this slide here, you know, this is telling, you know, how many magnitude 5.5s were less than 20 kilometers away. It was 0, right? So it's like, but we did have 180 magnitude 4 or greater within 40 kilometers, which is pretty good, you know, as far as a statistical sampling. But so that's one of the questions, though. Is there a scaling law, right? I mean, you know, at all, and it's sort of that even that question, I don't think we can answer it. But it sort of looks like there is, right? But even and the same thing in the Google study, right? If you look here in the channel tuning, where they went for magnitude 5 and greater. So here they turned the dial up a little bit and said, okay, now you in order to qualify for this study, you need to be greater than magnitude 5, right? And near a station pair. But you'll see the training set only had 3 earthquakes and the test set only had 4 earthquakes. So, you know, it's which is on the edge of and there's text in the paper about this, but you're kind of getting towards the edge of what you can fairly do the statistics on, right? Whereas with blue or flathead, it's the statistics are more reliable.
Excellent. Thanks, Karl. One last question is, so you've talked all about magnetic fields. Have you seen any work that's looked at electric fields, and do you think there'd be value in adding that to the mix?
Yeah. So when I started working with the QuakeFinder team, you know, the first thing I said was, well, you know, you got these extra channels on your you know, data loggers. The first thing we have to do is put out electric dipoles. And you know, what was responded was, well, how about the first thing you do is the best you can with the data we have today, and then we'll talk about adding, you know, hundreds of new sensors to our array. And I get, you know, it was a good conversation, and I'm glad we did the work we did with what we had. But I think adding electric dipoles to the stations, they have the channels. You could do that, and then you could study other things too, right? Then you could study changes in resistivity, and all there'd be all kind of other opportunities. So I've seen electric studies reporting changes, and but we did not do a statistical study of that, and we don't have the data available. And it would be great to see the array get augmented with that data.
Awesome. Thanks, Karl. I guess it looks like questions are wrapping up, but I've got maybe 2 more for you. In terms of the data, are the data actually available? So you talk about, you know, these studies that should be done. Can students pick them up and start running?
So they can. It's an ambitious task, but you can. So 2 comments on that. Number 1, the total field data already compressed into total field is available. There's a link, and I shouldn't have stopped sharing. Just bear with me while I share, but I'll so the total field data is available, and it is in the manuscript. You'll find links and some you know, a miniature tutorial on how to access it. Oops. So and then basically, if you wanted to get beyond the total field data, you would have to contact QuakeFinder for that, and I'm sure that they would be open-minded to data sharing on that. But yeah, so there's a data availability statement in the paper, and so the data set is available. It's on Google Cloud, and it's in a Google bucket. And here's some you have to install GSUtil, and then away you can go and start pulling data down. And I think we specifically, you know, warn users about, you know, not like pulling all the data being sort of an ambitious task, but it's there. And so, but if someone was serious about analyzing the whole data set, I'd urge them to contact, you know, Dan Schneider and dschneider@quakefinder.com, and that would be probably an easier way. The way we delivered the paper to Google was, I think we put the data on disks and drove over to their office.
Yeah. Yes, a good way to get data from one place to another. Fair enough.
It's an old school transfer.
Reliable. Excellent. Well, cool. Thanks so much, Karl. This is a stimulating talk. Very much appreciate it. So we'll get the recording up on the MTNet site. And if you're able to share your slides with us, and we can get those posted up as well. So see lots of thanks coming in on the chat. And so thanks again, Karl. Much appreciated.
Okay, great. Yeah, thanks very much.
All right. See you later.
Cheers.